Hello all. So in this segment, we're going to be talking about entropy. It's an important component of the thermodynamics that we have alluded to, but haven't really discussed more precisely yet. So let's look at the learning objectives for this lecture segment. We're going to be recognizing when entropy is increasing in chemical or physical processes, when it's decreasing, of course, as well. Describe and use the Boltzmann equation for entropy, and calculate entropies of simple crystals and ideal gases. So let's go back a bit. We've talked a lot about exothermic and endothermic reactions. An exothermic reaction is one that releases heat from the system into the surroundings. An endothermic one is the one that requires heat from the surroundings to move in for that reaction to be possible to happen. It jumps up in energy, so it needs an energy input. So why do endothermic reactions occur? I mean, they require heat to be added. It seems like that would not, you could imagine that if it heated something up, then it would happen. But why would there be endothermic reactions that happen just on their own? And so one term we use here is spontaneity, the idea of spontaneity, the idea that once a reaction starts, it proceeds without continuous external influence, like heating it up. So really, when we talk about a reaction occurring, we talk about it being spontaneous or not. An endothermic reaction that I posted a video of before, we usually do a demo of it, but alas, barium hydroxide octahydrate plus ammonium nitrate reacting to produce barium nitrate plus ammonia plus H2O. And if you recall, this was an endothermic reaction. It actually sucked up enough heat from the environment that it actually could freeze the beaker to a wooden block. So it's an endothermic reaction. The change in enthalpy is positive. The standard change of enthalpy is positive. And so what is it that makes this reaction happen? Why is it spontaneous if it's actually climbing in energy instead of dropping down in energy? And the key to this is entropy. So we'll be talking a lot in the next two lectures about entropy and especially how to quantify it. So we'll start on that this lecture. We won't really sort of complete the story. We'll never quite complete the story. We won't get a full picture of the story until the next lecture. So entropy is essentially a measure of disorder. It's a little more complicated than that, but entropy as disorder is a good way to think about it a lot of times. For example, ice does not have very much entropy because the water molecules are locked into this hexagonal arrangement where they're making as many hydrogen bonds as possible. Whereas liquid water, you got hydrogen bonds being formed a lot of the time, but the molecules slide past each other. And finally, in steam, the molecules are behaving like a gas, and they're not interacting with each other very much. They're completely free to move around. So that is more disordered and higher entropy. And so the phases usually see a series. Solid is the low entropy phase, liquid is a medium entropy phase, and gases are a high entropy phase. So let's revisit that reaction about what's going on. So if we actually put the phases in, remember this is a reaction where you mix together two solids, and it became like a slurry, because what would happen is you have barium nitrate, but you also had ammonia gas being released, and H2O liquid being released as well. So it was going from something that was entirely solid to something that had a lot of liquid and gas as well, and like a solvent, an ionic solvent dissolved in the liquid. That's pretty disordered as well compared to solid crystals. So the two factors are energy and entropy. Processes proceed to lower energy, delta H is less than 0. If a system is exothermic, it will tend to proceed in that direction. Some exceptions we'll talk about later. And processes also proceed to more disorder when the entropy increases. So either when the enthalpy decreases or the entropy decreases. We won't talk about exactly how to combine them. What if the entropy increases, but the enthalpy also increases? What do we do in that case? We'll talk about that next time, about how to balance those two effects. But those are two effects that can push a reaction forward. The fact that it becomes lower in enthalpy, i.e. it's exothermic, or that it increases in entropy. So in this case, we start with all solids, end up with gases, liquids, ions dissolved in water, definitely a higher entropy state. And that high entropy is enough to compensate for the fact that it is an endothermic reaction. Okay, so entropy in different processes. So if water evaporating is a good case, it needs to take thermal energy in. And when that happens, if it's hot enough, it'll spontaneously vaporize. Or salts, ions dissolving in salt, you go from an orderly sodium chloride ions in a crystal lattice to disorderly being dispersed throughout the entire solution. So clearly there is a loss of order there. So now we want to sort of revisit and go back to the second law of thermodynamics. Remember the first law, one phrasing of it, you can't win. You cannot, the energy is conserved. The second law is that not only can't you win, you can't even break even. That reactions proceed spontaneously in the direction that increases the entropy of the system plus the surroundings. And so the entropy of the universe increases, and spontaneous process, so a spontaneous process again proceeds on its own without any continuous external influence. A non-spontaneous process takes place only in the presence of a continuous external influence. So that's the key is the entropy increasing. So entropy increasing, all processes incur a total increase in entropy. If the system plus the surroundings. Sometimes the system might decrease in entropy, but it will be accompanied by an increase in the entropy of the surroundings. So some spontaneous processes that are driven by the energy, a ball rolling downhill, it's losing potential energy, metals oxidizing, iron rusting or copper gaining or green patina because the copper and iron oxygen bonds are stronger than the bonds inside the metal. Gases dissolving into liquid, right? They don't have interactions outside, but then when they interact with the liquid, they gain interactions. Water freezing into ice at low temperature, that happens spontaneously because of the ability to form the hydrogen bonds. But driven by entropy, a gas dispersing from a small container to a low container, dye particles spreading out if they're dropped in, spreading out through like an entire swimming pool till it's completely dispersed. A hot system reaching thermal equilibrium with the environment. That is also a process that is driven by entropy. An important thing here is that spontaneity has nothing to do with speed. So we think of the reactants, the products, and of course the kinetics are determined by the intermediate states, and those describe the speed at which the reaction occurs. But whether it's spontaneous or not is solely a measure of its initial and its final state. Is the final state more stable or less stable than the initial state? An example, rusting iron. It's quite highly favored. It's a very exothermic process, but it's extremely slow. If you have iron powder, you can actually get iron powder to burn and release a lot of energy because there's a huge amount of surface area. But if a nail there, even though over time you'll release a lot of energy by rust occurring, it ain't going to happen fast. So it's important to remember the difference between the speed of a reaction and its spontaneity. Something can be spontaneous, but very, very slow. So higher temperature always leads to higher entropy. If you have higher temperature, you have more heat, therefore more movement. More movement, the molecules are visiting more places, they're jiggling around more, and the more places visited by the molecule, more entropy. So if you look at the entropy of a solid as a function of water as a function of temperature, it'll go up slowly as the molecules vibrate more and more. So it is a temperature-dependent property. At a certain point, you melt, and there's a big jump in entropy. And again, the entropy slowly goes up as the liquid molecules jiggle around more and more. At a certain point, you'll get a big jump. At the boiling point, you'll get a big jump to gas. And there also the gas increases in entropy as the temperature increases, as they're visiting more configurations.